and welcome to this lesson on trigonometry, compound and double angles. This lesson is obviously for grade 12 learners because the first time you're introduced to compound and double angles is in grade 12. So what are we doing in today's lesson? Well, we're going to look at a little bit of grade 11 trigonometry revision, just because you will need some of those concepts when you are faced with your grade 12 trigonometry. So we will go over those as part of the grade 12 compound and double angle section. All right. We're also going to be looking at just solving some of the problems that you get with compound angles, and then also looking at solving some of the problems with double angles. Now, when you think about a compound angle, what is it that a compound angle does? What is it? Does it make sense? Where do you see these compound angles? And that's the kind of thing I'd like you to start thinking about. Where would you imagine that compound angles are being used, and why is it that we need to study these compound angles? Why are they so important? I'd like you to think about that, and then also just consider the following explanation that's on your screen. There's an expansion of a compound angle, right? And you just need to state if you agree or disagree and what you would have done differently. I'm going to give you 2 minutes to have a look at this, and then we'll come back and go over it together. Right, so in this question we were dealing with a compound angle. How do we know that it was a compound angle? Well, the two angles were subtracted. So when you have two angles either being added or subtracted to give you a whole new angle, that's what you call a compound angle. Now, before we talk about this question where you had to analyze and see whether you agree with this explanation, let's talk about what a compound angle is. Where do you find compound angles? Well, you will always get compound angles being formed at the intersection of two sloping lines. So that's where you will get compound angles, and it's often used in woodwork. Woodwork, they use lots in carpentry, they use lots and lots of compound angles. You can imagine when they try to build chests of drawers and wardrobes and those kind of things, there's going to be a lot of points where lines are going to slope and intersect, and whenever they slope and intersect, you will see that there is a compound angle. So that's where we see them also in building, and we know that trigonometry is used a lot in building and engineering. Now, when we look at cos of 180 degrees minus 120, and we had to say, well, is this compound angle expansion correct? Now, you can imagine that if you were to get something like this wrong in practice, it could lead to lots and lots of expensive problems. So I've got cos of 180 minus 120. And you see that what's happened in this explanation is we've distributed. We've known from before that if I have a 2, say for example, outside a bracket, I would normally just distribute the 2 into the bracket, right? And I'll get 2a plus 2b. That's from algebra, so we're kind of used to that. So we see, okay, well, there's a cos here outside this bracket, so surely I can just multiply it in, and then it will become cos 180 degrees minus cos 120 degrees. And then I can say, well, cos of 180 on my calculator or using special angle diagrams, that's going to give me minus 1. Cos 120 is cos 180 minus 60. And then I can use the reduction formula to see that that gives me negative cos 60. Cos of 60 is a half, again using your special angle diagram or your triangles. And then we see minus a half times minus 1 gives me positive a half. So minus 1 plus a half is negative a half. Seems to be correct. I was able to distribute in algebra. Why can I not distribute in trig? Well, in trig, that cos actually has a meaning. Cos joined to an angle has a meaning. Cos by itself means nothing. So I can't just say cos. Cos of what? It's got to be followed by an angle. So cos of 180 minus 20, it's not like you're taking just a placeholder for a number and timesing it into numbers. No, you're actually taking a ratio, a function, and timesing it through, and that is what's incorrect here. Also, we can see just following through and finishing the sum off, I can see that cos of 180 degrees, if this is correct, the way we've done it here, I should get the same answer if I say, well, let's work out the brackets. 180 degrees minus 120 degrees is cos of 60 degrees. And cos of 60 degrees, you can put that into your calculator or use your special angle diagrams. That gives me a half. And I see, aha, these are not the same thing. And yes, the only difference is the minus, but that's a big difference, is it not? Would you rather like a negative account balance or a positive account balance? Those are two completely different things. Minus a half is not equal to a half. Therefore, you can see that by distributing the cos through the bracket, you actually get an incorrect answer to the solution, for the solution that you should be working out. Okay, so just talking a little bit more about what a compound angle is. As I said to you, when two angles are added or subtracted to give you another one, it forms what we call a compound angle. So just it makes more sense if we see it in a diagram. So for example, if I call this P and Q, and we see that that's labeled O, and if you've got angle alpha there and beta there, then the sum of the two, so angle POQ, will be equal to alpha plus beta, and that would be your compound angle. So angle POQ would be an example of a compound angle because it is the sum of two other angles. All right? What we saw from the example we did is that a trigonometric ratio cannot be distributed to the angles that lie within the brackets. So we know that we cannot say that cos of alpha minus beta is the same as cos alpha minus cos beta. So there must be a way that we can actually expand that, because imagine if you couldn't find cos or sine of an angle and all you would need to do for compound angles each time is to draw 90 degrees. It's not going to be possible. So we need to have formulae that we can use for compound angles. And this is where we can actually prove using the distance formula and the cosine rule, the cos rule from, you'll remember from triangles and your 3D trig that you did last year, the cos rule. The following compound angle formulae can be proved using distance formula and the cos rule, all right, for solving triangles. So we can show that cos of alpha minus beta is cos alpha times cos beta, and importantly, the important thing here is the plus, all right? So have a look at that. That's the important thing there. We've got cos of alpha minus beta is cos of alpha times cos beta plus. So what you see happening is that the sign is changing. So we go from a minus there to a plus there, and that's an important thing. You know, often when learners do these questions, they go through them quickly and they make silly mistakes by forgetting that if the sign between the two compound angles is minus, then your expansion is going to have a positive when we're dealing with cos of the compound angle. So similarly, cos of alpha plus beta will be cos alpha times cos beta minus sine alpha sine beta. And then sine alpha minus beta, we can show you, you can work it out, the expansion is sine alpha cos beta minus, you see the sign stays the same, cos alpha sine beta, and sine of alpha plus beta, sine alpha times cos beta plus, so the sign stays the same once again, cos alpha times sine beta. Now all of this, when you just see it in that form, doesn't make sense. It's just, you know, it's just expansions, it's just formulae. So we need to be able to use this to help us work out the answers to certain questions. So for example, if I've got sine of 105 degrees, okay, and I need to simplify that and to work out what is the answer to sine 105 degrees. Well, I can rewrite 105 as a compound angle, so as the sum of two other numbers. So I can rewrite 105 as 60 plus 45. Now you should recognize that as special angles. So I just want to at this point remind you of the important angles that you learned last year, the special angles, 30 degrees, 45 degrees, and 60 degrees. Any combination of these special angles, right? You can have any addition or subtraction combination of these special angles, and you can use compound angles to help you work out the solution without using a calculator, because these will often say without a calculator. So if I rewrite 105 as 60 plus 45, then using the formula, that one there, I can rewrite this compound angle into its expanded form as sine 60, because it's sine of the first angle, times cos of the second angle, plus we keep the sign, cos of the first angle, so cos of 60, times sine of the second angle, so sine of 45. All right. As I said, these are special angles, so you can use your special angle diagram to work out what the values are. If you do that, you'll see that sine of 60 will give you root 3 over 2, times cos of 45 is 1 over root 2, and at this point I should remind you, because some of you will be using a calculator, and you'll see that you'll get an answer of root 2 over 2 for cos of 45. They are equivalent, so you can use either 1 over root 2 or root 2 over 2. Okay? Plus, we've got cos of 60, and cos of 60 is a half, times sine 45, which is 1 over root 2 or root 2 over 2 if you rationalize the denominator. So that's going to give me, because my denominators are the same, I can simply add the numerators together. So they're both 2 root 2, so it's over 2 root 2. And I've got root 3 plus 1 over 2 root 2 if I add that together. All right, so if I add those two fractions together. So remember those important combinations. You saw that 105 was the sum of 60 and 45, and those were special angles. And there's lots of those that you will see as you go through and practice your questions. There's also 75 degrees, which is the sum of 30 plus 45. You'll see 15 degrees, which is the difference between 45 and 30 degrees. So those special angles are so important to remember when you are doing these compound angle questions. Okay, at this point, I think it is a good time to take a break, give your minds a little bit of a break, and then we'll come back and do some questions on compound angles. Welcome back, everyone. So we are looking at compound angles, and later on we'll have a look at double angles. Now, in the first segment, I reminded you about your expansions for all your different compound angles, and you're going to need to remember those expansions as we attempt question 1. So I'm going to throw it over to you and give you 2 minutes to have a look at the first question. Now the question you've just had a look at is quite a typical question for exams and tests, where you are given an angle and then you've got to break it down into its component compound angles. So if you look at an angle like 75, that's the sum of, and you start thinking about what special angles can I relate to 75. So 75 would be, immediately what comes to my mind is 30 plus 45 degrees. Before we look at this question, I just want to remind you, or just show you, maybe you weren't aware, of where you can use compound angles to help you simplify when you see certain angles. So for example, in the first quadrant, 75 will be 45 plus 30, right, as a compound angle. In the first quadrant again, 15 would be 45 minus 30, or even 60 minus 45, right? Depending on whatever you see first, both of them would be correct. Another one that you might see, which we started off with, is 105, which is 60 plus 45. And that's in the second quadrant. Okay, and if you go through these, you will see that what I'm trying to get at is there's certain angles that you should automatically and immediately realize and recognize that I can break these either by first using reduction and then break it down into its component compound angles. All right, so it's ones that you really need to be looking out for. If you can see them, it makes life much, much easier to solve these sorts of trig questions. And you know, as I said to you before, you might have one where you first have to use your reduction. So you've got to say 180 minus something else first in order to see your compound angle, okay? But remember to always look for it, especially now that you are in grade 12. These, I guarantee, will be thrown in. So you need to always be looking for those compound angles when you are dealing with reduction. Okay, so how do we do this one? I'm going to rewrite 75 degrees as a compound angle. Compound meaning the sum of two things in this case. So 75 is the same as 45 plus 30. Okay, so I've taken 75, I've rewritten it in that bracket. I now then need to think back and call up my formula for sine of alpha plus beta. Okay, I'm not going to have enough space there, so let's just move that a little bit further down. So if I have sine alpha, or A, let's just use A, sine of A plus B, that's going to be sine A cos B plus cos A sine B. That's the expansion, right? So I can take sine of 45 plus 30, apply that identity to the compound angle, and see that my expansion is going to be sine of the first angle, so sine of 45, times cos of the second angle, so cos of 30, plus, we keep the sign the same, cos of the first angle, so cos 45, times sine of 30. All right. So we've got that. I've just used my identity and I've now expanded the formula. Again, we're dealing with special angles, so you can actually call upon your diagrams. You know, I have no problem with you then using your calculator and working out, okay, sine of 45 is equal to root 2 over 2. I've got absolutely no issues with that. If you prefer to do it on your calculator, you can, but often these questions will say without a calculator, and that means you need to remember your special angles. So sine of 45, it can be root 2 over 2 or 1 over root 2. For now, I'm going to write it as 1 over root 2. It will just serve this example quite well. Cos of 30, using your calculator or using your special angle diagrams, you will see that cos of 30 will give you root 3 over 2. Plus cos of 45 is 1 over root 2. And then sine of 30 is a half. Okay, we simplify this. So the first term, I'm going to get root 3 times 1 is root 3 over 2 times root 2, which is root 2 root 2, plus 1 times 1 is 1 over 2 root 2. And this gives me, because my denominators are the same, I can keep the denominator and add the numerator. So this gives me root 3 plus 1 over 2 root 2. And I think, yay, I'm done. But actually, you're not done, because you need to go back and read the question. That was not the form that they had asked you to show. So is there anything wrong with my answer that I got? I got root 3 plus 1 over 2 root 2. Is it wrong? No, it isn't wrong, but you haven't completed, you haven't finished, you haven't answered the question. So what it would mean in an exam and test situation is you would lose unnecessary marks. So how do we take it from what I've got to what it is that they actually require? Well, we have to do something called rationalizing the denominator. Now, when you rationalize the denominator, you are trying to get rid of the surd in the denominator. You're trying to get rid of the root sign. So I see that in my denominator I have a root 2. So I want to get rid of that root 2. How do I do it without changing the overall value of this expression? I times by 1. Another way to write 1 is root 2 over root 2, because root 2 divided by root 2 is 1. So I'm going to get in the numerator root 2 times root 3 plus 1. I'm going to leave it like that, because for me that suits our purposes, because I saw that that was how the answer was given in the question. And now if I multiply 2 root 2 times by root 2, well, the square root of 2 times the square root of 2 is the square root of 4. And the square root of 4 is 2. So 2 times 2 is 4, and that now looks like what they asked you to prove. Okay, so be very careful that you answer the question completely. Okay, just be very careful. Make sure, go back and check and make sure that you have written your answer the way the examiner or the teacher would like to see it. All right, I think it's time for another question. So here we're going to give you another chance to get these compound angles perfect. So this is question 2. You're going to do this using only using compound angle formulae that you've learned so far in today's lesson. So even though you might be able to do this with double angles, we haven't discussed that yet, just use compound angle formulae and without a calculator, and we will give you 2 minutes to do this. Okay, welcome back everyone, and I hope that you thought about this really well and came up with a good reasoning on how to do this using just the formulae that we have learned in today's lesson. Okay, so there is a very quick way to do it, but we're not going to use that very quick way. So what I'm going to do is just split this up and show you cos squared 15 can be written as cos 15 times cos 15 because we are squaring, right? Minus sine squared 15 is sine 15 times sine 15. Now I write that out and I think, well, I've got cos minus sine of the same angle. Does that look familiar to me? Well, kind of, except for I know that my expansion for cos of a plus b, usually the a and b are different values. So if this was cos a plus b, I'd get cos a cos b minus sine a sine b. It doesn't matter that these are now the same value. So a and b are equal. They're both 15. That doesn't matter. We can still use this expansion. Okay? So cos of an angle times cos of an angle minus sine of the same angle times sine of that same angle. I can now say, well, I can go backward with my formula and I can rewrite this before expanded form as a compound angle cos of 15 plus 15. The reason I can do that, well, it's just using my expansion from my formula. I've got this part of it, cos A cos B minus sine A sine B. So this is like my A, and that's my angle B. All right. So I can just rewrite this in the formula as cos 15 plus 15, which is then cos of 30 degrees. And cos 30 is equal to root 3 over 2. Okay. All right. So think about that as we go into our next break. All right. Think about this compound angle and how, even though those compound angles had the same value, so they were really double angles, right? They had the same value, so we could double them up. And think about that as you go into the break, and then when we come back, we will discuss this relationship about double angles, what goes on there. That comes up after this. Welcome back, everyone. I hope that you are refreshed after your break and you were thinking about the concept of double angles using that example that I've just shown you before the break. Okay, so what is a double angle? Okay, and we saw that our formula for a compound angle can really be used as well when dealing with double angles. So double angles mean that we're going to have two of the same angle that we are using as our compound angle. All right, so we've got formulae that we have developed that have been derived from those compound angles, you know, that we saw right at the beginning of the show. We've used those formulae to help us develop formulae for double angles, and you can be tested on these formulae in your tests and exams. So what am I talking about? I've got sine of 2 alpha, so it's called a double angle. So it's 2 alpha, two of the same angles. The expansion for that is 2 sine alpha cos alpha. How do I get that? Remember, we know that sine of A plus B is equal to, you know, that whole expansion that we've looked at just now. It's sine A cos B plus cos A sine B. We've seen that. What happens if A and B were the same thing? So let's say it was both just angle A plus A, and that's perfectly acceptable. There's nothing wrong with that. I would then be able to write this as sine A plus A, which means I'll replace all my B's here with an A. So it becomes sine A cos A plus cos A sine A. But hang on, these two are exactly the same thing. Okay, cos A times sine A times cos A, those are the same things. So therefore I can add the terms together to sine A cos A. So it gives you 2 sine A cos A if you add those two terms together. And that is how you can derive from your compound angle, you can derive the formula for sine of 2 alpha or sine of 2 times any angle for your double angles. Similarly, you can show that cos of 2 alpha has 3 different expansions that you can write, and they all are equivalent. So you can either have cos squared alpha minus sine squared alpha, 1 minus 2 sine squared alpha, or 2 cos squared alpha minus 1. Okay, so there are 3 separate expansions that are equivalent forms of cos 2 alpha. All right, how do we use this? How do we put this into practice? Well, if I've got 2 sine 15 degrees times cos 15 degrees, so I've got this part of the formula, I know that I can go backwards and rewrite this as sine of 2 times my angle, and my angle is 15. So that's going to give me sine of 30 degrees, and that will be a half. All right, so you see how simple these compound and double angles make calculations. It can really simplify life quite a bit, especially for those questions where it says without a calculator. So it's time for you to have a go at a few questions. I'm going to give you a chance to look at this one. This is a very quick one, so I'm only going to give you a minute. Okay, so here it was just a straightforward application of the formula that you had to use, okay? You had 2 cos 2 alpha times sine 2 alpha. And let's write this as sine of a compound angle. So I know from my formula that if I've got sine of 2 alpha, that's the same as 2 sine alpha cos alpha. Okay, as long as these angles are the same, you can then use your double angle formula. All right, so here I've got 2 alpha times sine of 2 alpha, so it's cos 2 alpha times sine 2 alpha. These two alphas are the same. So using this expansion, I can say that this is going to be the same as sine 2 times the angle that you are dealing with. So it's not going to just be alpha. Here we had 2 alpha and 2 alpha, so it's sine of 2 times 2 alpha, which would be sine of 4 alpha. Okay, and what's interesting here and what you need to remember, because you can be asked this in both ways, you can also go this way, in this direction, and get to that answer. Okay, similarly, 2 sine theta over 2 cos theta over 2, so using my expansion, it will be sine of 2 times the angle, which is theta over 2. So 2 times a half theta, because theta over 2 is really just a half theta. Those 2's cancel, and I just get sine of theta. Okay, so again, importantly, we can rewrite and go this way. So sine of theta can be written as sine of 2 times theta over 2, and then you can write that as 2 sine theta over 2 cos theta over 2. Okay, so we can go both ways with these expansions, and it's important that you remember that. All right. Now remember, when we started this little segment on double angles, we had lots of expansions for the cos of 2 times an angle, right? So I want you to think about those expansions and decide which one to use. In order to do question 4, we will give you 2 minutes to have a look at this. Okay, so we know that for the cos double angle identity, there were three different ones that we could have chosen from. We have been given the expansion of cos 2 alpha, cos of 2 times an angle, is equal to 2 cos squared alpha minus 1. That's what we've been given. We've been given this right-hand side of the identity. Okay, so I can go backwards using my identity and say, well, 2 cos squared alpha minus 1 is the same as cos of 2 times alpha. So 2 cos squared 22,5 degrees minus 1, I can rewrite as cos of 2 times the angle, 22,5, and cos of 2 times 22,5 is cos of 45 degrees. Again, you see those special angles coming in, right? So cos of 45 degrees is 1 over root 2, or equivalently, if we rationalize the denominator, root 2 over 2, both are acceptable, unless you ask to write your answer a specific way. All right, really quick way to get to the end of this example, right, or the end of this question. And if you know your compound and double angle identities really well, you can just use them from your head, but you also get given these on formulae sheet. All right, time for the next question, and this is often where learners get a bit trapped up and they don't know, okay, well, which do I use? And that's the section of proving identities, because then they don't know what to choose for cos of 2 alpha. What is the double angle identity that I should go for when I've got cos of a double angle in my proving an identity question? Okay, so that's one where a lot of problems come up, and that's what we're going to deal with now in this next one, and show you tricks and ways that you can actually decide what to use for your expansion of cos 2 times an angle. I will give you 3 minutes to do this one. All right, guys, so this is one where I know that a lot of learners often have difficulties because they're not sure what expansion to use for cos your double angle identity. And it is one that gets better with a lot of practice. You've got to do a lot of questions before you see it automatically and you start seeing the pattern. But I'm going to give you a little bit of an idea of how to approach these questions. So when you're starting with these proving an identity questions, you want to separate your left-hand side and your right-hand side. We want to show that the left-hand side is equivalent to the right-hand side. So I've got 1 plus sine 2 beta over cos 2 beta. And I'm happy with the sine 2 beta because I know that there's only one double angle expansion there, right? So I can write this as 2 sine beta cos beta. Most people are happy to get to that step. And then we've got cos 2 beta in the denominator. Now we've got to decide, well, what do I change this to? And there's 3 different ones to choose from. And what I always say to learners is let what you are asked to prove guide you. So here we are asked to prove that this is cos beta plus sine beta over cos beta minus sine beta. So the expansion that you want to use for cos 2 beta is going to be the expansion that includes both cos and sine. I'm not even going to try and go for any of the other ones. I'm going to go straight for the cos squared minus sine squared identity. So I'm going to make this cos squared beta minus sine squared beta. And that's really straight from cos 2 beta, that comes straight from your identity, is equal to cos squared beta minus sine squared beta. That's straight from your identity. That's where I get that from. All right. I have a look at this and I see, okay, well, at the bottom I can perhaps factorize that because that's a difference of 2 squares. But at the top I'm kind of stumped. There's nothing really more I can do except one big thing that we can do. We can rewrite the 1. And there's lots and lots of different ways to rewrite 1, especially in trigonometry. I can rewrite 1 as sine squared plus cos squared. We know this identity. It's the most famous one in trig, the one that most of you remember. I can rewrite this 1 as sine squared plus cos squared beta. So sine squared plus cos squared is 1. I haven't changed the value in the numerator, and you always got to bear that in mind, that you're not changing the value of any of the expressions as you go through your identity. Okay? Now I've got sine squared plus cos squared. I'm going to just rearrange that in the numerator so it's easier for you to see. So it's sine squared beta plus 2 sine beta cos beta plus cos squared beta. Okay, so it's easier for you to see the trinomial that's hidden in there. All right, and then at the bottom, for now, we're not factorizing anything as yet, so I'm just leaving it as cos squared beta minus sine squared beta. Now the trinomial that's hidden in the numerator, sine squared beta plus 2 sine beta cos beta plus cos squared beta, the trinomial there is in brackets. Remember your trinomials, you're going to have the sum of the factors of your first and your third term must add up to give you your middle term. So sine squared beta is going to be sine beta times sine beta in each of the brackets. And then my second term is cos squared beta, positive, so it's going to be plus cos beta plus cos beta. And if I were to add those terms up once I've expanded, so that means I'm going to get plus 1 cos beta sine beta plus 1 cos beta sine beta. If I expand, that does indeed give me 2 sine beta cos beta in my numerator. All right, at the bottom, cos squared beta minus sine squared beta, that's a difference of squares. So it's the square root of the first term minus the square root of the second term times square root of the first term plus square root of the second term. And then you look at that and you get really happy because you can see that you've got common factors in the numerator and denominator. And I know all of you love doing this. You can cancel those common factors. They divide out to give you 1. So overall, you're just left with sine beta plus cos beta over cos beta minus sine beta. And that, importantly, is equal to the right-hand side. So you have managed to prove your identity. Okay. All right, so hopefully you all follow that and you understand a little bit better of how to approach questions that involve cos of a double angle. Okay, we've done quite a lot in today's lesson, so a very quick summary. We just looked at all the different expansions for our different compound and double angles, and you have those given to you on your screen. I'm not going to read through all of them, but the important thing that you need to remember is when you're dealing with cos of a compound angle, you need to change the sign between your compound angle and your expansion. All right, thank you so much for joining me today. I hope that you've learned a lot. Until next time, cheers.